Alrighty, folks. So this is going to be the first warm-up question that's actually on our kinematics practice 3, but it is a bit of an all-encompassing one. So that's why we want to kind of take a little bit of time, break down everything, and you can actually see all of the different pieces and how we can start approaching kind of complex problems like this. We're going to have a ball that's thrown straight up into the air with a speed of 25 meters per second. We are ignoring air resistance. This is really important. We'll come back to it later. We want to know two things about this ball's motion. First, what is the maximum height of the ball, and then how long does it take for the ball to actually hit the ground? So if we think about we're throwing this ball upwards, it's reaching its highest point, and then it's going to fall back down. Okay, and we want to know two things. First, what is the maximum height of the ball, and then finally, how much time does it take, for it to go all the way up and come back all the way down? Okay, and so because these are two different styles of problems, we're going to look at this in two main chunks. Okay, the first chunk is going to be the ascent all the way to the top. The second chunk can maybe be the ascent back or the descent back down. Okay, so to get us started, let's first determine the maximum height of the ball. Okay, to get us started, I always like to make a little template. Okay, where we can talk about maybe the initial height, the initial velocity. We could talk about the final height, the final velocity. And in order to solve this problem, the only other things that we're going to want are maybe time and acceleration. Okay. Now, the nice thing about this type of problem is this is essentially a free fall problem. If we are thinking about anything that's being thrown into the air and falling, we know that at any point along this arc, the only thing that's interacting with our ball at any stage is going to be the Earth, right? So the force of gravity, the interaction between the ball and the Earth, that's the only thing acting on our ball. We can ignore air resistance, and this makes things a lot easier to conceptualize. And if we have an object that's in free fall, right, it's free of air resistance, the only thing it's interacting with is going to be gravitational pull from the Earth, we can assume the acceleration. Okay. Now, when things are just falling, right, we said the acceleration is 10 meters per second per second. Okay, that's kind of our constant. But if we fill in the variables we have, right, our initial position, 0, initial velocity is 25 meters per second, okay? Because our ball is moving upwards, if I assume everything going up is going to be positive, everything going down is the negative direction. As our ball gets higher and higher and higher, we know its speed starts to slow down, okay? And that's because it's experiencing, in this case, a negative acceleration, okay? But that acceleration is still constant, negative 10 meters per second, or negative 10 meters per second squared, okay? And so that just means that our ball is going to slow down at a rate of 10 meters per second every single second that it's in the air, okay? So now that we have these pieces, we can also assume one more detail. Okay, think about the ball as it's traveling all the way up. We know its speed is going to get slower and slower and slower. We also know that on the way down, it's going to get faster and faster and faster, which means at its highest spot, as the speed gets slower and slower and slower and slower, at the very peak, its velocity is going to be 0 meters per second. This is just for a moment. It's just the moment between when it's moving up and when it falls back down. There's this brief moment in time at the highest position where its velocity is 0. So if we're thinking about this first chunk, okay, our initial velocity was 25, and our final velocity at that height is going to be 0. So I'm going to put that here, 0 meters per second. Okay, so we have quite a lot of information to roll with. We are just looking for the final position or the maximum height in this case. So we just have to identify which of our formulas is going to help us get there. Okay. I notice that we're still missing time. So any formula that contains time is probably going to be useless to us because we're just missing too much information. But if we look at this third equation, we actually have everything we need except for the final value that we're looking for, right? We have the final velocity, we have the initial velocity, we have the acceleration. The only thing we're missing is that change in position. So I'm going to go ahead and rewrite this formula just so I've got it. And instead of writing this out, I'm just going to simplify it and say change in position, okay? Because that's going to be the same thing as like my maximum height. So now we're just plugging in the variables that we have, okay? My final velocity is 0, so I can plug that in for final. Initial velocity is 25. We do have to square that value at some point. We're going to add that to twice of our acceleration, which is negative 10 meters per second. And we're going to multiply that by our overall change in position, right? This is the one thing that we're missing. So from here on out, it's just algebra, okay? So if we're going to solve this out, 25 squared, I'm getting 625, right? So 625, and we're going to add that to 2 times negative 10. Well, that's just negative 20. And we're going to multiply that by our change in position. Let's subtract 625 from both sides. Okay, so we end up with negative 625 is equal to negative 20 times our change in position. All right, divide both sides by negative 20. Okay, and so 625 divided by 20, we're getting 31.25. Okay, and that's going to be equal to our change of position. In other words, our final position, right? Because we start at 0, we have a change of 31.25 meters. That's the overall change of position. So that is going to be our maximum height. Okay. And again, we did that by assuming a couple of things. All we had was the initial velocity of that ball. But because we are dealing in a frictionless environment, we can assume a couple of things. We were able to assume that the acceleration of the ball is going to be negative 10 meters per second. And we know that at its highest point, our ball is a temporary velocity of 0 meters per second. So plugging in those values can get us to our maximum height.